Speakers, Cecilia Cormick, Institute. Have you all, please?
Okay. Okay. Hi, everybody. Thanks to the organizers for the chance to give this talk. I'm not gonna give the talk that was announced. I will present something different, which is newer, and I thought it would fit the scope of this meeting better. It's called Hamiltonian Amplification, and it's a collaboration with this bunch of people, Christian Arends, Dennis Bonda, Herschel Rabitz. Christian is with full name here because he did most of the work, and Daniel Burgard in Aberystwyth. I want to start with a couple of clarifications. First clarification is a geographical one. I'm in the National University of Córdoba in Argentina. I say this because most Europeans think of Spain when I say Córdoba. So Córdoba is also a city in Argentina. It's here, and it has a very large university. That's where I work. It's also the oldest university in our country. And the second clarification is about the content of the talk. This is an area in which I am a total outsider. So I did work on this, but it's not my area of expertise. So I chose it because I thought it was closer to the main topics of these meetings. But if you want to know very technical stuff, I will probably not be able to answer. Anyway, I found it fun to work on this, but I just want to make this clear. This is not my kind of work. So the talk is about speeding up quantum evolution. And it's a topic which can, so the main result can sound enormously natural for many people and surprising for others, depending on their background. So there were a lot of discussions while we were working on this, whether it was entirely trivial or surprising. It depends on where you come from. So many people find the idea very counterintuitive that you can actually do this. But what we did is, in the end, very simple. The math is absolutely easy, and we think it could have applications if people think about it more seriously. So why do some people find this surprising or counterintuitive? So the problem we considered is, let's say you have a system with some Hamiltonian h, and you want to make it go faster, just the same but faster. So you want the Hamiltonian to be amplified by some prefactor lambda, which you take to be larger than 1. Of course, if you have full control of your system parameters and you know them all, then this is a trivial task. You just move up all the parameters by a prefactor lambda. But what happens if you either don't know all the parameters or you do not have full control over all of them? Then we don't know if it's even possible to amplify the Hamiltonian. So that's our question. Can you do that? Now, the standard strategy for people coming from quantum control seems to be, I'm not from quantum control, but it seems to be to consider a set of unitary operations and think about just applying operations from this set, then letting the system evolve freely for a while, and then applying the inverse. And doing this with all the unitaries in this set in such a way that you have a scheme like this, where you have unitary, free evolution, the inverse, and so on. And if you do this very, very fast, you can transform your Hamiltonian onto something like this, right? To first order in delta t, you can just group all the transformed Hamiltonians and get an effective kind of averaged Hamiltonian that has this form. And this is done a lot, mostly for dynamical decoupling, which is something I will come back to later. It can be used for for dynamical decoupling of both finite and infinite dimensional systems. And if your system is finite dimensional, you can use this to reduce your Hamiltonian. So you can slow down the evolution. There's a very simple example of this, which is a qubit whose Hamiltonian is proportional to some projection of the spin. If you take that set of unitaries to be the different Pauli operators or the identity, then by commuting them with this, you see that you flip signs in some cases. So you can make parts of the evolution cancel out, and with this you can reduce the speed with which the system evolves, or you can freeze the evolution, at least to first order in t, well, delta t. But it's clear to see that if you have a finite dimensional system, you can never do this to amplify the Hamiltonian, because this sum here cannot have a norm which is larger than the Hamiltonian which you started with. So you can slow down the evolution, but you cannot amplify it. You cannot make it go faster. For infinite dimensional systems, this norm restriction doesn't hold. The problem is, okay, it's trivial that it doesn't hold, but most people in quantum control have always thought about finite dimensional systems. So most people never actually considered the idea of making things go faster by this kind of trick, because from the very beginning they thought that it would never work. But actually finite and infinite dimensional systems do behave very differently in some respects, and we already knew that some infinite dimensional systems cannot be slowed down. So this idea of just canceling terms in the Hamiltonian so that the evolution goes slower cannot always be applied to infinite dimensional systems. And it turns out that if instead of wanting things to go slower, you want them to go faster, then it's better to have an infinite dimensional system. You cannot do that with finite dimensional systems, but in infinite dimensions, you can. So I want to start with the simplest example, which is just a harmonic oscillator. Let's say you have a harmonic oscillator with a frequency you don't know. So this is what this picture is supposed to represent, is the rotation in phase space. And you don't know the frequency, which is the only free parameter here. And you decide to take that set of unitaries that I mentioned before to be squeezing in x or p direction. So what you do is you apply squeezing in x, you let the thing rotate a bit, then you anti-squeeze, and then you do the squeezing in the other direction, and so on and so on. It's just, it turns out this accelerates the evolution by a prefactor hyperbolic cosine of 2r, where r is the squeezing parameter here, okay? So this is the form of the unitaries that do the squeezing in x and p. Again, everything I say so far is to first order in delta t, then I will comment on the errors. The reason why this works is absolutely simple. The squeezing operation just transforms these operators like this. So x is multiplied by some prefactor, and p is multiplied by the opposite prefactor. So you have a transformation like this. And when you do the squeezing in the other axis in phase space, you have these prefactors exchanged. And if you do this very, very fast, in practice what you get is an effective average of these two transformations, so that x is amplified to something that goes like the hyperbolic cosine of r. And p does the same, and any other phase space quadrature is amplified by the same amount. If instead of considering these operators, x and p, you think of x squared and p squared, then you see that it's the same idea, except that the prefactor is the hyperbolic cosine of 2r. That's it. There's nothing else, but it works. And so the Hamiltonian is amplified by this prefactor, at least to lowest order in delta t. This can be generalized to multimode Hamiltonians. So if you have a Hamiltonian of this form, coupling several modes, but coupling only x with x and p with p, then it's also very simple to see that it will work. So you can do this to more general Hamiltonians than that of a single harmonic oscillator, but it's not the most general quadratic Hamiltonian, because terms of this form are left invariant. This is something people asked before. You can choose to squeeze in a different phase space direction so that these terms are amplified. But if you do that, then there is some other quadratic term that doesn't get amplified. So we haven't been able to come up with a scheme that would amplify general quadratic Hamiltonians. This is the most general Hamiltonian that we have been able to amplify. But still, we think it's pretty general. So there are many situations in which Hamiltonians of this form are relevant. So that was the basic idea. As you see, it's extremely basic, but still something many people had never thought about. Now come the technical improvements on it. First of all, we thought there's no way to do things infinitely fast, so that the operation is applied in an infinitesimal amount of time. So now we consider, instead of a sudden squeezing operation, a smooth Hamiltonian. So the control is now the squeezing Hamiltonian as before, but now it has a prefactor here which amplifies or reduces the squeezing and chooses whether the squeezing is in the x or p axis. And if you take this to be a delta function, then you recover the previous case. But now we consider something which is more general and more realistic, because this is, in principle, bounded. We don't need to put a Hamiltonian which diverges or anything like that. And we pick this Hamiltonian so that the evolution associated with the control Hamiltonian alone is periodic. So we do that because then, if we move to a rotating frame, which is rotating with this control Hamiltonian, the effective evolution of the system has a periodic Hamiltonian, okay? The Hamiltonian is periodic in the rotating frame, and then we can make an expansion in delta t of the evolution when we consider both system Hamiltonian plus controller Hamiltonian. So, because we want to be still able to do this expansion in delta t. Well, it turns out you can choose this function r of t in such a way that you can amplify, of course, but also you can pick them so that the second order correction to the amplification cancels out. This calculation can be done exactly because everything is quadratic, so everything is very treatable. And if you cancel out the second order correction, then the convergence with delta t is much, much better. So this makes the method work much better than with the original simple bang-bang. So we started thinking of smooth pulses out of realistic conditions, but it turns out it's a better idea in terms of results. And here are some results regarding the convergence with delta t. So because the result I showed you is just perfect for delta t infinitely small, we compared the target accelerated Hamiltonian with the one we get from the actual finite sequence. And this is the error as a function of delta t for some just test case, which is very simple, which is a single harmonic oscillator. And this yellow line is what you get with the bang-bang scheme. So when the pulses are applied suddenly and infinitesimally fast, infinitely fast. And this blue curve is the one with the smooth pulses with the same amplification factor. So you see, it works much better. But then in order to make this estimation a bit more realistic, we also considered the case that the control Hamiltonian has fluctuations, so it's not a perfect control Hamiltonian. And this, at some point, makes the error saturate. So if you have some fluctuations in the control Hamiltonian, at some point you cannot do better than some limit, and you have some error that comes from your action on the system, which is not surprising. Then the other thing is, you could think, if I can amplify my system Hamiltonian, I can use this to defeat decoherence. If I want to go faster than the decoherence rate, I can make my system go faster, and hopefully the decoherence rate will stay the same, and then this will make my evolution more coherent or something like that. It turns out, if you think of it like that, it doesn't work, because I already told you, you amplify operators like x or p. So if you have a standard kind of coupling with your environment, like you have a system of harmonic oscillators and you think of an environment of harmonic oscillators as well, this is the typical kind of coupling that you would use to model the interaction with them. And this x operator is amplified. So this can also be seen as an amplification of the coupling constants with the environment. And it turns out you amplify the decoherence rate by roughly the same amount as you amplify the system evolution. So the ratio stays more or less the same. So if you want to defeat decoherence, at least in this context, you are not gaining anything. But people have proposed to actually suppress these couplings by using dynamical decoupling. The idea of dynamical decoupling is very simple. It's just if you are able to apply a parity operation in your system, so you flip x to minus x, and you do this all the time, then this essentially averages out. So this is done a lot with the spins. It's not so common for continuous variables, because applying these parity operations is not so trivial for continuous variables. But if you want to do this, you can combine the acceleration of the coherent part of the Hamiltonian, or like whatever is your desired part of the Hamiltonian, with dynamical decoupling to suppress some bilinear couplings. And this is the kind of sequence that you would have in that idea. So it gets more complex. Now, I said people don't really use this so much because it may be very complicated to apply the parity operations in practice, but it was also shown recently that it's also doable to replace the parity operations, which have to be applied suddenly, with the smooth fluctuations of the system frequency. You can take these fluctuations of the frequency in such a way that the result is still dynamical decoupling. That's a bit more complicated, but experimentally it sounds a lot more feasible than the parity. So far, that's essentially the result. Now, I spoke so far only about quadratic Hamiltonians. That sounds very restrictive, but there are lots of examples in which qubit systems have interactions that are mediated by harmonic modes. So people would, from quantum control, say you cannot amplify interactions between qubits unless you have full control of the parameters. But if your interactions are mediated by a harmonic mode, then you can use these tricks on the harmonic mode and amplify the effective interactions. Because your real system is not finite dimensional, it's just your effective system that is finite dimensional. So you can use this to amplify interactions in finite dimensional systems when you do not have control over the interaction strength directly, but you have control over the mode. So as an example, you have typically the trapped ions, where you have the vibrational modes, and also superconducting qubits coupled to cavity fields. So we took this as an example case and did some numerics, where actually Christian Arendts did the numerics. He took a system of superconducting qubits coupled to a cavity modes, and he chose this example because people working with these systems can do squeezing operations very well. So this is absolutely demonstrated and kind of trivial for them. We do not know how easy it is for other implementations. And he numerically simulated the evolution of this system, applying these squeezing operations in the bang-bang scheme. So what I plot here is the probability of swapping the states. So we start with a state like this, and we calculate the probability of ending up with a state like this as a function of time and as a function of the squeezing parameter R. So you see that if you apply this squeezing, you can reduce the time that it takes for the qubits to flip. Now, the parameters were taken from realistic superconducting qubits experiments. And the disappointing part is that we need a delta t, which is enormously small. It's absurd. So like this, the scheme can never work. So it works in theory, but nobody will be able to really do this in practice. But we already know that using smooth pulses, the convergence is much, much better. The problem is we could do the calculation of how smooth pulses should be for the harmonic case, because the harmonic case has all quadratic Hamiltonians, the evolution is linear, you can solve for everything. Here, you cannot really just sit down and do the calculation, because your system is not linear anymore when you have the qubits. So we think there is a lot of room for improvement here by optimizing over the pulses that we have, but it has to be done numerically. It's just more complicated. At some point, we will do that part, but it has to be done specifically for the setup that you have. Once that your full evolution is no longer linear, there is no recipe for having the best smooth pulse that will do the work for you. Now, this slide about related work is at the end because of our own development of the work. We were thinking about these ideas, and because we come from the theory, we were not very sure that nothing of this is doable at all. And then we found out that there are some other groups proposing to use squeezing to speed up the evolution in manners that are pretty similar to what we proposed, either with superconducting qubits or optomechanics or trapped ions. It has taken a while because the squeezing operation is not very trivial to apply, but it turns out all these groups have found out that in their particular setups, it might be a good idea to use squeezing to speed up the evolution. So the point is all these proposals are very specific to those particular setups. So they are designed to work for those systems. And what we find nice about our own work is that it's just very conceptual. It's not attached to any individual application. And we think it would be nice to have some overview of what these different theories have, what these different proposals have in common, and frame everything in terms of using squeezing as a resource to speed up the evolution. It's all work in progress because as far as we know, this is the first time that people from quantum control start thinking about this kind of continuous variable setups. So this has been a very short talk, I know, but this is because that's what it is. The main conclusions are that the intuition that you build from finite dimensional systems is not generally valid. This, for us, was like the main message, because we've been discussing with people a lot, and people in quantum control just never thought of speeding up things because they had this previous idea that it was impossible. And I showed you that there is an important family of continuous variable Hamiltonians that can be amplified even if you don't know the parameters, and even if you do not have access to all the parameters in the Hamiltonian. You only need local control of the subsystems, and you can still enhance the interaction strength. The smooth bounded controls also work better than the first idealized proposal with bang-bang. That's good, because they are more doable. And the method can be combined with dynamical decoupling, assuming you can perform dynamical decoupling, which is a different story. And the other thing that we find to be more promising is the fact that you can use this to amplify couplings in hybrid systems, which have both finite dimensional and infinite dimensional components, so that an effectively finite dimensional Hamiltonian can also be amplified. And this is a fantasy slide about things that we dream would be possible if this was actually going to work. So this one is the Daniel Burgard favorite. This is why it's there, but we don't really know how to do it. It's just, hey, there's this idea that nobody had before, and let's hope that people in quantum control will try to explore this more. We think of this as more of an open door to do something new in the field, and let's see if it actually goes somewhere. And this is the person who did everything, who is Christian Arendts, now a postdoc in Princeton. And I finished earlier because I thought it was 25 minutes, but now you have plenty of time for questions or for coffee. Thanks.
Thanks, Cecilia. Well, we have plenty of time for questions before the coffee break, so we are open for questions. Oh.
Actually, I have two questions. So the first one is, experimentally, people can squeeze